Hello, Luke. Welcome to lesson 73. So today we're going to be talking about factoring the difference, of two squares and the probability without replacement. So two topics for today. So to begin with, let's start with the factoring one. Now, again, we just seem to continually come back to factoring here. There's so much to learn with factoring. And there's so many tools that we're going to try to keep adding to our toolbox on how to factor. So we've done these till we're blue in the face, I think, at this point. If I have a trinomial such as this and I ask you to factor it, the first step is to look and see if there's anything common that you could factor out among the three terms. In this case, there is not. So then you would look to see if it's in a form that you're familiar with. And in this case, it is. It's got the x squared followed by a term with just an x followed by a term without an x. And when we see that, we always want to try to factor this into binomials. All right, so we do our set of parentheses and we do our x's. And in this case, we have a positive sign, so they're both going to be the sign, positive. And we have a 2 and a 2. And we end up with x plus 2 times x plus 2. Okay, that's, again, something that we've been doing for a very long time now, and we should just be doing these in our sleep. We're going to move on, though, today, and we're going to look at a different scenario, okay? A different scenario. So we're going to look at a new tool to add to our toolbox today when it comes to factoring. All right, so what in particular what we're going to be looking at is not a trinomial like the last one was. The last one we started with a trinomial, 3 terms. Now we're actually looking at a binomial, 2 terms, okay? And when we have 2 terms such as this, we're going to find that there is a way to factor this, okay? The thing that we need to recognize is that this binomial is actually what we call a perfect square. A perfect square, okay? And the reason it is a perfect square is because the first term and the last term, the first and second terms, they are both, how would I say it? Square rootable, if that makes sense. They are both a product of a variable with itself, okay? Or it could be a number with itself too, depending upon what these terms are. So what I mean by that is that this is actually an x that is being squared, right? And then we're subtracting from that a y, which is being squared, okay? So we're taking an x and squaring it, and we're taking a y and we're squaring it. So when we have both terms as a square of something, then we call that a perfect square. All right, they both have to be squared though. So for an example, this would not be a binomial that is a perfect square. If I had something that looked like this, x to the third minus y to the second, okay? Here, I have an x, and it's being raised to the third power. Well, that's not what we would say is square rootable, okay? It's not something that's being multiplied by itself, twice. It's being multiplied by itself 3 times in this case, okay? Now, the y squared does fall into a square category, but it's not both terms. And in order for something to be a perfect square, it needs to be both terms. Okay, so because this one is not a perfect square, then the whole binomial is not a perfect square. Okay, now, if I were to give you something that looked like this, would this be a perfect square, do you think? X to the fourth minus y to the sixth. Okay, think about that for a second. Would this be considered a perfect square? What do you think? Yes? No? Well, let's look at it. Could it be written in the form of something squared minus something squared? That's really the question we need to ask. And if it can be written in this form, then yes, it is a perfect square. Okay. All right. So is there something that I could put into this first set of parentheses such that it still equals x to the fourth? I can't change that. But is there something that I could put in here? And the answer is yes, there is. If I put in x squared, right? X squared, and then that being squared, would give us x to the fourth, right? Because when this exponent is outside the parentheses, then the exponents inside the parentheses get multiplied by it, right? Remember, that's the rule for exponents. So this is an x to the second, which would be the x to the second times 2, which is x to the fourth, which is what we want to get. So here, clearly, there is a way to write this as a set of parentheses being raised to the second power. How about y to the sixth? What would go in this set of parentheses? Well, think about it. What would go in there? Y to the third, right? Because 3 times 2 is 6. All right? So, once again, we have something that is being squared here, and we have something that's being squared here. So both first and second terms are being squared here. So this would be a perfect square. Okay. All right, very good. So that is kind of the first step here. We need to recognize when expressions can be thought of as perfect squares. All right, and there really is no way around it. The only way that you're going to know how to do these is by first recognizing that what you're looking at is a perfect square. So you really have to be disciplined. You have to use your critical thinking and look at a problem. And if they tell you to factor it, you need to walk yourself through all of your tools. You need to say, well, is there anything in all of the terms that I could factor out? And if there is, great, then do that. And if that doesn't work, then say, is it in a form that I'm familiar with? And if it's in this form, like this one, then you could say, okay, I can try to get it into these binomials. Okay. If it's in this form, then you can say, okay, it's a perfect square. And if it's a perfect square, I'm going to now show you how to factor it. Okay. So a perfect square, we'll change color here. To factor a perfect square, like the trinomial, we are going to have a set of parentheses. All right, so we're still going to be factoring this into two binomials. The question is just how do we do it? And it's actually really simple, okay? And the answer is we take this first term, similar to the trinomial, and we split it up. We take its square, I should really say, or kind of the square root might be the better way to put it. We kind of take the square root of this term, and we place that in the beginning of our two parentheses. So we have an x in the first and an x in the second. Then we go to our second term here, which in this case is y squared, and we do the same thing. All right, we take the square root of that, and we put 1y here and 1y here. Okay, the only thing left is the sign. Okay, and the sign is always going to be opposite. One's going to be minus, one's going to be a plus. Okay, now you might say that this negative sign maybe clues you in on that, if that helps you to remember. This negative sign right here means opposite. All right, so you know you're going to have opposite signs. That's a good way to remember it. One pitfall to avoid here is this perfect square. Factoring, I should say. This factoring of a perfect square only works if this sign is negative. I'll say that again because this is really important. This is a common mistake that people will make. This method of perfect square will only work if the sign is a negative between the two terms. Okay, that's why in the beginning we called this factoring the difference of two squares. Difference means subtraction. All right, difference is the answer to a subtraction problem. So we're taking the answer of a subtraction problem of two squares. So two squares are being subtracted from each other. That's what we have here. So if I had written this as x squared plus y squared, and asked you to factor it, You would not be able to. Okay, you cannot right now because this would not work. I cannot do this. I can't say, oh, this is an X and an X and a Y and a Y and oops, that's kind of a Y. That's a terrible Y. Let's fix that. It looks something like a really atrocious X. Okay, so we have our Y, and you might be tempted to say, oh, this is a plus sign, means they're the same, so we're just going to add 2 plus signs right here. Okay, no, that's not going to work. And to show you that it's not going to work, let's do a quick FOIL. All right, so let's take the first. We get an X squared. We take the outside, which is a plus XY. We take the inside, another plus XY. And then we take the last, which is a plus Y squared. We combine any like terms here, and we end up with x squared plus 2xy plus y squared. This is not the same as this. Okay, we did not get back to where we started, so something went wrong in our factoring. And the problem is this negative, or this middle term. This middle term showed up, okay? And we didn't want that middle term to show up. But there's no way around it. There's no way to get rid of that middle term because all of the signs here are positive. And so, you know, if you want to get rid of something, usually you want to subtract it out. And in this case, you can't subtract anything out. There isn't any subtraction. So you're always going to have that middle term, okay? That's why it only works with the negative sign. Because if we think about it in terms of the negative sign, let's go and we'll FOIL this one next and see what happens. So here we have x squared for the first, and then we have outside, which is plus xy. Inside, notice the difference here. The inside is a minus xy. And then the last is y squared. And notice what happens here. We have a positive xy and a negative xy. They eliminate each other. You plus xy, you minus xy, they're gone. And all that we're left with is x squared plus y squared, which is what we started with. Okay? So that's why it works. It only works because of this negative sign. It's so important. Without the negative sign, you don't end up with these two middle terms canceling out. Okay? And just to kind of complete the argument, you might say, well, what if I were to write this instead as x minus y, x plus y? Why won't that work? And I'm sorry, not minus y plus y. Let's use both minuses, okay? We need a minus, great. We'll put 2 minuses in. X minus y, x minus y. Maybe this plus means they're the same and they're minus. Well, if you do that, again, if you FOIL it, you're going to end up with x minus xy minus xy plus y squared. And these are not going to eliminate again. The only difference now is it's minus 2xy plus y squared, which again is not the same as this. Okay? So you can see, or no, excuse me, not the same as this. That's what we're trying to get to. So you can see that it does not work. Okay, that middle term needs to go away. And the only way it'll go away is if this sign is a negative. Okay, so watch out for that pitfall. All right, so with all that being said, let's try a couple of these problems and see how you do. So here is a problem. Go ahead and pause the video, try this one on your own, and then we'll see if we can do it together here. All right, so the first thing to do is to recognize that this is a perfect square. Okay, if you can't see that, you won't know what to do. All right, so the perfect square here, what is it going to be? In order to show that it's a perfect square, we need to, again, set up our parentheses. We want something squared minus, notice the minus sign. That's a good sign. We need that. Something squared. That's the form that we want to get it in. And if we can get it into this form, then it is a perfect square. And then we can factor it. Okay, but first we have to make sure it's a perfect square. So, could this be written as something raised to the second power? Well, sure. It would be written as 3x. Right? Check that. 3x raised to the second power. Well, that would mean that it's 3 to the second power x to the second power. Remember, when this exponent is outside the parentheses, it means everything inside has to be raised to that power. Okay, so 3 to the second x to the second, which is going to give us 3 times 3, which is 9, and x squared is x squared, which is where we started. So clearly 3x raised to the second power is 9x squared. So great. The first part of the problem is done. We've checked one part anyway. Now let's check the other term. Could this be written as something squared? Sure. 6 squared, right? 6 squared is 36. So there, we've proven now that this is a perfect square. And only once we've proven that it's a perfect square can we proceed with the factoring. Now, eventually you'll be able to do this part in your head. Okay, you'll be able to just look at it and say, oh, I see that as being a 3x squared and then a 6 squared. So it's a perfect square. All right. But for right now, I think it's good to write out the parentheses and just try to prove to yourself that this is a perfect square. Once you've proven it to yourself, then you can go ahead and factor it. So now we will factor this out into our two sets of parentheses. And we just simply take the square root of this 9x squared, which incidentally is the number inside the parentheses. These are the numbers that we're going to be using. Okay, so this 3x we're going to place here, and we're going to place here. This 6 we're going to place here and here. And then as far as signs go, remember one of these is a positive, one of them is a negative. Doesn't matter which order you put them in. We'll go negative, positive. And that is our factored solution to this problem. All right, and again, you could FOIL it and double check. You'll see the middle terms cancel out, and the first term is going to give us 9x squared. The last term is going to give us a negative 36. All right, very good. Let's try another one. Yeah, try this one. It's just a little bit of a different perspective. Give it your best shot, and don't worry if you didn't get it. We'll do it together. All right, so this one, it's a little bit different because you might say, whoa, wait a minute, Jim. We don't have our negative sign here in the middle. You just told me we can't do it if we don't have the negative sign in the middle. And I would say you're absolutely right. However, we could rearrange this because I do see a negative sign over here. Okay? So what if I just rewrite this? You know, I'll just use the cumulative property, which says I can switch things around. So this would be 4n squared minus 16m squared, right? It's the same thing. I've just switched the terms around. And now this negative sign has moved to the middle, which is where we want it. So at that point, I can ask you, is this a perfect square? That's the question. Is it a perfect square? Can I write it in some form that looks like this? Okay. And the answer is yes. I could write this as 2n. That would give me 4n squared. I could write this as 4m. That would give me 16m squared. All right, so now I'm ready to do my factoring. This is going to be my first term for both of these binomials. This is going to be my second term for both of these binomials. I have a plus and I have a minus. And we're done. Okay? Pretty straightforward. All right, try this one now. It's kind of the same procedure as the last one. Give it your best shot, and then we'll do it together. All right, so once again, we will need to recognize that in order for us to test this to see if it's a perfect square, we're going to first have to write it so that the negative is where we want it. All right, so we want it in the middle. So it's 49b squared minus 36a squared. And now we can check this. Is this a perfect square? So let's put our parentheses, raise them to the second power. What would we put in? Well, this one could be a 7b, right? This one could be a 6a. And there we go. Now the hard work is all done. Now we just need to write our binomials here. First term goes at the beginning of both. Second term goes at the end of both. And we have a minus and a plus, and we are done. Okay, so once you've recognized that it's a perfect square, you can see finding the factorization of it is actually really easy. You just have to remember the process. All right? All right, let's try this one. Go ahead, pause the video, give it your best shot. All right, you should be well aware of this trick now. We first need to rearrange it, get the minus sign in the middle. Minus 36x to the 6th, right? Now we can look to see if it's a perfect square. So we have our parentheses raised to the second power. And we're kind of taking the square root of this. The square root of 25 is 5. That works. The square root of m10. Now we have to bear in mind what we're trying to do here. We're trying to take this exponent and divide it by 2. All right, that's really what we want to do, because over here we're going to be multiplying it by 2. So can we take this exponent and divide it by 2? Sure, it's an even number. So anytime you see an even number in the exponent, you know that you can find the square root of it. If it's an odd number, you're stuck. But if it's an even number, you can find the square root. So what's 10 divided by 2? 5. So this is going to be m to the 5th. Okay, then over here, the number is easy. That's 36, the square root of 36 is 6. Watch out, it's not 36 divided by 2. Be careful, we're talking square roots. All right, and the square root of x to the 6th is going to be the exponent divided by 2, which is very different than saying 36 divided by 2. So we're taking the exponent divided by 2, which is 3, which will give us x to the 3. And you can do a mental check on this if you want to. So if you were to check it, you would say 5 squared is 25. M to the 5th squared is m to the 5 times 10, which would be m to the 10th. And same with the second term. All right? So now we can go ahead and put this into our binomials. And we have our 5m to the 5th, 5m to the 5th, 6x to the 3rd, 6x to the 3rd, and a minus and a plus on these, and there we go. There it is. All right, so let's try this one. Why don't you pause the video, try it yourself, and then we'll do it together. All right, so once again, they try to confuse us a little bit by throwing the subtraction sign in the beginning. We're going to rearrange this so that we have our subtraction sign in the middle. Okay. And then we need to check to see if this is a perfect square. So if it is a perfect square, we should be able to write it in this form. So let's look. Well, the square root of 49 is 7. The square root of a squared is just an a, so that works. The square root of 36 is a 6. Square root of x to the 6th, now that's going to be x to the 3rd, right? Square root of y to the 4th is going to be y to the 2nd, right? Okay, so we can write it in this form, so it is a perfect square. Then we can go ahead and actually write out the binomials. So the first term will be the first term here, 7a. We're going to have a plus and a minus, or you could do a minus and a plus, either way. And then the last term is going to be the 6, x to the 3rd, y to the 3rd. I didn't give myself, not to the 3rd, to the 2nd. I didn't give myself a lot of space here. X to the 3rd, y to the 2nd. All right, whoops, 6. 6x to the 3rd, y to the 2nd. And there we go. All right, so hopefully that makes sense to you. I think at this point we're ready to move on. We're going to talk about the probability without replacement. So we are completely switching gears here, going to something completely off topic, which is again back to probability, which we discussed in a couple of previous lessons. All right, so up to this point, we've been talking about only probability problems in which there was what we call replacement. So in other words, if I have, let's just, I don't like that. Let's go a different color here. if I have a, let's say I have a bucket, all right, and let's see here, bear with me. We're going to make some red marbles, let's say, okay? So, whoops. Let's just say we've got a couple of, red marbles in here. Let's say five red marbles. And then let's also say we've got a couple of blue marbles. So we've got 1 marble, 2 marble, 3 marble, and we'll just say 4 marbles that are blue. Okay. Now let's say I tell you to close your eyes, dip your hand into this bucket, and pull out one of the marbles. Okay. You're going to pull out one of these marbles. What's the probability? So let's change this color. We'll just go black. What's the probability of getting a red marble? And this is a common way to ask probability questions. We have the P, which represents probability, and then in the parentheses, we have the desired outcome. Okay, so what's the probability of getting a red marble if you were to close your eyes, dip your hand into the bucket, and pull one out? Okay, well, how many desired outcomes would satisfy this question? Well, we have 5 red marbles in here. So we have 5 possible outcomes that we want. And then we have 4 blue. So we have 9 marbles altogether, right? So we have 5 possible outcomes that we want, desired outcomes, out of the 9 total outcomes, because there are 9 marbles in here. Okay, so the probability is 5/9 that we will get a red. Okay, now let's just say we do that. So we dive right in and we pull out a red. Hooray! We had a 5/9 probability of getting that red, and we got it. Okay, very good. Now let's say this was just the first trial right here. But let's say we have a second trial. All right. And I say, okay, what's the probability of getting a red? We already know that. It's 5/9. Well, then what happens if I pick again? I want to know what's the probability of picking another red. Okay. Well, in order to answer this question, we need to ask, well, is this experiment, or these experiments, are they being done with replacement, or are they being done without replacement? So in other words, I just picked out this red marble. The question that we need to ask is, well, is this red marble staying out, or is it going back in? Do I put the red marble back in and then select again? All right. And then that's really what we've been doing up to this point. Whenever we've had these sorts of scenarios, we've always said, well, you pick out a marble, and then you put that marble back, and then you mix them all up again, and you pick out another one. All right. And if that's the case, well, then each trial is really going to be independent from the other ones. So we're doing the same trial every time, and there isn't any effect from, left over from previous trials. So if the first trial I got a red, well, that's great. I had a 5/9 probability of that happening. Now, if I put that marble back and then I say, okay, now we're going to do it again, what's the probability of getting a red this time? Well, it's still going to be 5/9, right? Because nothing has really changed. We still have the same number of marbles in here, the same number of red, the same number of blue, and we're just dipping in and trying to pick one out again. So the probability remains 5/9. Okay. So what's the probability here if we talk about consecutive events? What's the probability of me pulling out a red and then dipping in again and pulling out another red? Okay. Well, with replacement, maybe I'll write that up here. This is with replacement. With replacement, it's simply going to be 5/9 for the first experiment times 5/9 for the second experiment, right? Because remember, that's how we find the probability of multiple consecutive events. All right, if we need to pull out a red twice, well, the probabilities for each is 5/9. So to figure out what's the probability of me actually getting a red twice, we would multiply those probabilities by each other. And we'd end up with 25 81 over 81, right? So 25 over 81 would be the probability of me selecting 2 reds in a row if I'm replacing, if I'm putting that marble back when I'm done. Okay, so, but now, what about if we do not have replacement? So let's say we want to go without replacement, which is really what we're trying to get to in this lesson, without replacement. Okay, this is with, this is without. So without replacement, well, that means we're taking, our first trial here. We're going to dip in. What's the probability of getting the red for the first trial? And then we keep that out, assuming that it's a red. We'll go to our second trial. What's the probability of me getting a red this time? Okay. Well, if I'm not replacing, things change a bit, don't they? So if I dip in and I am fortunate enough to pull out a red, okay, what was the probability of that happening? Well, it was, again, it's the 5/9, the same thing as it was before. Nothing changes. 5 correct marbles, or I should say 5 desired marbles out of the total 9 marbles in the jar. Okay, so 5/9 is the probability. Now, if I pull out that red, I can say, all right, I'm on the road to completing this successfully. I have to pull out 2 red. I succeeded in pulling out 1 red. What's the probability of me pulling out a red a second time if I do not put this marble back into the jar? Okay, so if I do not put it back in the jar, well, that's going to affect this second experiment here. All right, because now there are fewer red marbles to take. All right, we've already pulled one out. So that changes everything. If we look at it now, what's our sample space here? What's the desired outcome? It's red. So how many reds do I have? There are 4 in here. So there's 4 ways in which I could get a red marble. Out of how many marbles are there altogether? Well, now there's no longer 9. There's 8 of them now because 1 has been already pulled out. So it's 4 out of 8, which could be reduced to 1/2. Okay. So I have a 50-50 shot at this point of selecting a red marble. Okay. Which is very different than the 5/9 probability before. I had a better than 50% shot the first time. Now I only have a 50% shot of getting that red marble. Okay. So what's the probability of me then, actually succeeding and getting 2 red marbles in a row? Okay, well, again, we use the same thought process here. We have to take the probability of the first experiment and times that by the probability of the second one to determine the probability of these 2 things happening in this consecutive order. Okay, so we have 5/9 times 1/2. So now the probability is 5 over 18. Okay, so in the first scenario, when we had replacement, the probability was 25 out of 81. In the second scenario, when we do not have replacement, the probability is 5 out of 18. Okay, so hopefully that clarifies the difference between finding probability where there is replacement and finding it when it's not. When there's not replacement, there's a little bit more work involved because every new run of the experiment means we have to revamp the numbers and figure out the new probability for this latest experiment. Okay, because the last one is going to change it. They're no longer independent. Okay, they're no longer independent. When there is replacement, it's really easy because once you found the probability of the first trial, well then all of the trials after that are going to have the same probability because nothing is changing. So it makes it a little bit easier to compute. Okay, so hopefully that makes sense to you. All right, so tell you what, just to make sure that you've got this, I'm going to give you your very own problem. Oops. And I don't like the orange jar. I don't know why, but I don't like the orange jar. I like the black jar. So we're going to go with the black jar. And once again, I will give you some marbles. Let's go with maybe kind of this green marble. Make sure I get marbles. And we'll pop him in. Maybe 1, 2, 3, 4, 5, 6. Why not? And then we'll go, I don't know, what's your favorite color? Kind of this orangey gold. 1, 2, 3, 4. We'll do 4. 4 of those. All right. And I want to know, for my question here, I want to know what's the probability of getting a red, that would be 0. Probability of getting a green, followed by a green again, followed by an orange. Okay, there we go. I want to know what's the probability of getting a green, then an orange. Okay, in that order. So go ahead and pause the video, have fun with this, try to decide what that probability would look like. And by the way, this is going to be without replacement. Okay, so I do not replace them after I've pulled them out of the jar. All right? Okay, so give it a shot, and then we'll look at it together. All right, so let's see how you did. So we're going to first do the probability of selecting a green. Okay, that's the first step here in our consecutive order of events. So the probability of getting a green. Well, there are 6 greens and there are 4 oranges. So the probability is going to be 6 desired, 6 greens out of the total of 10. All right, so that's the probability of getting the green on the first one. If I wanted to reduce it, I could, but I'll just leave it at 6/10. Okay, now what's the probability of selecting a green the second time? Now remember what's happened here is we've removed a green. So boom, a green is gone. Okay, so now we need to say what's the probability of getting a green on the second attempt. Well, now that's changed because we're not replacing the green, and we have 5 green left over. So now it's 5 desired outcomes out of 9 marbles. The number of marbles dropped 1 from 10 to a 9. Okay, and the desired outcomes dropped 1 from a 6 to a 5 because we pulled 1 out. Okay, now we need the probability of an orange. So what's the probability of an orange? Well, the oranges, there are 4 oranges left in the, what? I'm sorry, I forgot to pull out a green. Gotta make sure we pull him out. Okay, so we pulled out the green for our second one. Now the probability of an orange, well, there are 4 oranges left out of the total of 8. So there are 4 out of the 8. Okay. And again, look at the denominator. They just dropped by 1. 10, 9, 8. Okay, because we keep pulling them out. Okay, so we pull out an orange. Okay, so now what's the probability of this actually happen? This is the desired event. The desired outcome is right here. Green, green, and then orange. What's the probability of that happening, of getting a green, green, orange? Well, to figure that out, we have to multiply all these probabilities by each other. So we have a 6/10 times a 5/9 times a 4/8, which just, I'm going to reduce that. Makes it a little easier in the multiplying. 1/2. Okay? And then we'll start multiplying some things out here. Now, I could just say this will reduce. 5 can go into itself once. 5 can go into 10 twice. So I'll reduce that. I can reduce this 2 into this 6. Take out some numbers there. And now I can even reduce this 3 into this 9. Right? So that should make it all easier to multiply. And the numerators now, all I have left is 1. Denominators, I have 2 times 3 is 6, so it's 1/6. So the probability of getting a green, green, and then an orange is 1/6. Which you might say, if I tried this experiment, these three consecutive draws, if I tried this experiment 6 times, in a perfect world, one of those times I would have gotten a green, green, followed by an orange. Okay? All right. Hopefully that makes sense to you. It's pretty straightforward. Definitely draw pictures if you need to. There's nothing wrong with that. I actually feel like the more pictures you draw, the better you probably will do. So don't feel bad or don't feel silly about drawing some sloppy pictures, even if you're not the best artist, and just using that to make sure that your thought process is clear and it's accurate. Okay? All right, very good. Well, we will stop here today, and I will see you tomorrow.